Reach into the dairy aisle and you can feel it on your wrist, cold air, spilling out over the edge and running down your arm. There is no door there. There never was. I'm Alex, and this is Unseen Systems. A refrigerator with a hole in the front of it should not work at all, and this one is holding food at 5 degrees Celsius in a room at 20. There is a door on that case, you just cannot see it. And it is expensive. Most of the electricity that case burns is not spent on the food inside it. It is spent on the warm, damp air of the shop that keeps getting dragged in. Which means that in energy terms, the thing in front of you is mostly an air conditioner for the supermarket with some yogurt in it. A researcher at the University of Washington who studies exactly this put a figure on it.
75% of the cooling load is attributed to infiltration of warm and moist air from the surrounding environment.
So start behind the shelves. The cooling coil is not at the front where you are standing, it is tucked in at the back and the bottom, out of sight. A fan pulls air across it, chills it, and sends it up a duct hidden behind the shelving. Some of that cold air seeps out through the perforated back panel and washes over the packets directly, but most of it is going somewhere else. It is going to the top of the opening. There is a slotted grill running along the top front edge. Engineers call it the discharge-grille, and out of it comes a flat sheet of cold air fired straight down across the whole open face. It falls the full height of the case and lands in a second grill along the bottom front edge, the return air grill, which swallows most of it and sends it back to the coil. Launched, falling, caught, chilled, launched again, that is the cycle the whole case is built around. The engineering literature has a name for what that sheet of air is doing, and it is not a metaphor.
Air curtains are created in open refrigerated vertical display cases for creating an invisible barrier between the cold air inside and the warm air outside the case.
But a moving sheet of air has a problem that a pane of glass does not. Air dragged through still air pulls that still air along with it. Little eddies form all down both edges of the curtain and mix the aisle into it. So the barrier leaks by its very nature, and the entire design problem is just how much. Every manufacturer settles on a slightly different speed. Not one of them escapes what is really being asked here, which is for a jet of air to behave like a wall. And a jet only behaves like a wall inside a very narrow window. Too slow, and the sheet sags and spills out over the front. That is the cold you feel on your ankles. Too fast, and it goes turbulent and starts scooping up the room. There is a band in between where it stays coherent, and the whole engineering effort goes into staying inside it. The launch speed, the angle between the two grills, and how smooth the air is as it leaves. Getting the turbulence at that top grill down from 14% to 3 cuts the leakage by roughly another tenth. Which is why so many ordinary things ruin it. A trolley going past, the store's own ventilation, a door to the car park opening, and the one you can actually see for yourself. Every case has a load line printed inside it, and product stacked above that line sits directly in the path of the jet and tears the sheet open. The curtain also gets warmer as it falls because it has picked up more of the shop by the time it reaches the bottom. And the moisture it drags in has to go somewhere too. It freezes onto the cooling coil, which then has to be defrosted on a cycle, which briefly works against the very thing the case is for. None of which the case can report to you, and the rule it is actually held to is not about the case at all, it is about the food, 5 degrees Celsius, in the carton. So here is the obvious question: doors exist. Glass doors on these cases cut the load by something like half or better, and they pay for themselves in a handful of years. So why is the front still open? Not because of physics, because of the reach. The open front takes away a step between a shopper's hand and the product, and the industry has long held that the step costs sales. Notice what that is: a belief about shoppers doing the work of an engineering requirement. Some stores go further and heat the floor of the aisle or run the ceiling heaters all year in that part of the shop, so that customers are comfortable standing in the cold ere the case is spilling. They pay for the same decision twice. And that decision does not stop at the shelf, because the cases have to be open and spread out where the shoppers are, The cold has to be delivered to all of them, which means refrigerant piped from a machine room at the back of the building out to every case in the shop and back again. Long runs, hundreds of joints. A pressurized gas circulating under the entire sales floor, which brings us to the failure mode of this system, and it is not a dramatic one. It is a slow leak that never really stops. A supermarket's refrigeration system is not charged with a few kilograms of gas like the fridge in your kitchen. It holds the better part of 2 tons of it, and a meaningful fraction of that goes missing every single year through all those fittings. The United States Environmental Protection Agency, which runs a program tracking exactly this, states the numbers plainly.
Typically, these refrigeration systems are charged with 3,000 to 4,000 pounds of refrigerant. They can leak in excess of 20% of their charge each year.
And here is the proof that this is a layout problem and not a refrigeration problem. Take the same technology and seal it inside one cabinet, compressor, coil and all, welded shut at the factory, and the leak rate falls below 1% a year. The gas is not escaping because refrigeration is leaky. It is escaping because we insisted on spreading it across a shop floor. Put the energy bill next to the shopping list, and the point of the whole thing moves. The interesting thing about that open case is not that clever engineering lets a fridge work without a door. It is that the missing door was never an engineering conclusion at all. It is a decision about how a hand reaches for a carton, and refrigeration was simply told to make it work. Because once you accept the open front, you have also chosen the cold sheet, the electricity that goes into the aisle instead of the food, the pipework under the whole shop, and the gas that goes missing every year. The physics is downstream of the merchandising. So there is a door on that case after all. It is made out of moving air, it is being rebuilt continuously, and it has been leaking since the moment the shop opened. When you walk past the chilled aisle and feel that cold spilling across the floor, that is not the case working badly, that is the door, coming loose exactly where it always does. Thanks for watching.